Hello all, I am Shatabdi Acharya from Vedang Institute of Technology. In this video, we will be taking up a very important organic reactions which is nucleophilic substitution reaction. So first of all, we will try to understand the name of this reaction which is nucleophilic substitution reaction. Now, what do you mean by a nucleophile? You can break it into nucleophile. Nucleo means nucleus, somewhat related to nucleus. We know in an atom, a nucleus is a positively charged sphere, right? So, and philic means loving. So, that species which is nucleus loving can be called as nucleophilic. Now, if the species is nucleophilic, that means nucleus loving, then in itself that species must be negatively charged because opposites attract. So, if nucleus is positively charged and that particular species is attracted to the nucleus, then it in itself it must be negatively charged. So, any negatively charged species is called a nucleophile. Okay, got it? Any negatively charged species, I can represent it generally as Nu minus. Okay, it's a nucleophile. Now, nucleophilic substitution. Now, what do you mean by substitution? Means taking someone's place. Taking someone's place. That means that particular place was taken up by some different atom, and when this nucleophile approached the species, then it basically removed that already existent atom and took its own place, took that atom's particular place. So this is called nucleophilic substitution reaction. So basically it deals with a group of reactions where in a chemical compound a nucleophile is replacing a leaving group, okay, which we call nucleofuge. Nucleofuge. So basically a nucleophile is replacing a nucleofuse and taking its place. So that group of reaction is called as nucleophilic substitution reaction. So this is a nucleophile. It's a general reaction which shows a nucleophilic substitution reaction. This is a nucleophile. This is the alkyl halide and this is known as substrate. Substrate means that particular organic compound to which the nucleophile attacks. Okay, so this is basically the attacking species. And this is the attacking site. The site of attack where the nucleophile will come and attack. What it will basically do? This nucleophile will attack the alkyl group, and obviously why this is happening? The root cause lies is carbon cannot exceed its tetravalency. Carbon has to form 4 bonds only. So what happens when this nucleophile attacks this carbon? Attacking means formation of bond, right? So if this nucleophile tries to form a bond with another substrate, then it has to remove something, remove one particular atom from that organic compound. So when this nucleophile attacks the carbon atom, it removes the X minus, which is called as the leaving group. This is the leaving group or the group which goes out of the carbon system. Okay, and we get a product where this group is replaced or substituted by the nucleophile. A nucleophile is a species with an unshared electron pair. It can be lone pair or any negative charge which reacts with an alkyl halide by replacing the halogen substituent. This is called the leaving group. In nucleophilic substitution reaction, the carbon halogen bond of the substrate undergoes heterolysis. Heterolysis means breaking off with different charges. For example, if it has to break, it will be substituted by a negative charge group. Therefore, the carbon has to be positively charged and the leaving group has to be negative charged. That means the leaving group has to move out with the pair of electrons. So, CX bond of the substrate undergoes heterolysis and the lone pair of electrons on the nucleophile is used to form a new bond to the carbon atom. Okay, as we have seen in the general reaction. Now, a nucleophile is any negative ion or any neutral molecule that has at least one unshared pair or unshared electron pair, a lone pair. General reaction for nucleophilic substitution with an alkyl halide by a hydroxide ion is shown here. This is the nucleophile, which is a hydroxide ion. It basically attacks this alkyl group. This X minus leaves we get an alcohol and a leaving group. Leaving group is our halide ion. To be a good leaving group, the substituent must be able to leave as a relatively stable, weakly basic molecule or ion. Which means if a leaving group is, suppose, detaching itself from the carbon system, why will anything try to go from a more stable state to any less stable state, right? If the carbon or the substrate is seeing, after I leave the carbon system, I'll move to a less stable state, then will it ever leave the system? Obviously no. So the leaving group must be relatively stable after it has detached itself from the carbon system or the organic system. In case of alkyl halides, the leaving group is the halogen substituent. It leaves as a halide ion. And if I see halide, then iodine is a very good leaving group. Iodide is the strongest leaving group because of its larger size. Okay, because halide ions are relatively stable and very weak bases, they are good leaving group. In general, halides are good leaving group. But if I compare halides, in halides also iodide is the most stable or very good leaving group. Now, okay. Now what happens? General reaction we have seen is there was a carbon substrate. The nucleophile was attacking. Now, I'm generally saying the nucleophile is attacking, but the attack can be of two types, right? First of all, what it can do is, this Rx is there, the nucleophile will come, it will see the X position is already taken up. So what it will do is, it will attack the alkyl group from the back side, from the rear end, right? It will attack the alkyl group from the back side, as a result of which what will happen? The alkyl group will push this halide group out, right? This is one possible way. The second possible way is, when the alkyl group or when the organic substrate sees the nucleophile approaching towards itself, what it can do? It by default will detach this bond and it will make this particular site already readily available for just this nucleophile to come and take up, right? So the first way was rear attack or backside attack, and the second is the Rx, which was already the organic substrate. What it will do, it will break off the Rx bond and it will make a carbocation already ready for this nucleophile to come and take its place, right? So it will keep this place vacant and just the nucleophile will come and attach itself on this, resulting in the formation of RNU bond. So there are two ways by which this substitution can take place. So considering these two ways, we have classified nucleophilic substitution reaction into two different categories. One is substitution nucleophilic bimolecular, substitution nucleophilic unimolecular, commonly known as SN1 and SN2 reactions. First of all, we'll see SN2 reaction. Here, why the name SN1 and SN2? These substrate, the number 1 and 2, is basically because of the rate of reaction. If the rate of reaction depends upon both the substrate as well as nucleophile, then the order of the reaction will be 2. Hence, the rate is, or the reaction is called as a SN2 reaction. See, the rate of the reaction depends upon the concentration of the substrate, which is methyl chloride, and the concentration of hydroxide ion. Okay, the nucleophile as well as the carbon skeleton, okay, or the substrate also. So as it is depending upon both these, therefore the name SN2, right? So the reaction is of a second order overall, and the reaction is first order with respect to methyl chloride and first order with respect to hydroxide ion. Now the rate equation is, the rate is proportional to CH3Cl as well as OH minus. We have just removed the proportionality factor with a constant K, which is a rate constant. Now, if I see the mechanism means what pathway the reaction follows. Okay, so what happens is, the nucleophile attacks the carbon bearing the leaving group from the back side. Okay, the first possibility which I was discussing. So what it will do, the carbon or the substrate is there, the nucleophile, when it will be approaching, it will see no space is available for it to form a bond with carbon. So what it will do is, it will attack the carbon from the back side. Okay, the bond between the nucleophile and the carbon atom is forming at one particular instance. This bond is forming and the bond between carbon and leaving group is breaking off, right? the configuration of the carbon atom becomes inverted during the SN2. Inverted. Why inverted? See, suppose here CX was there. Now the nucleophile is coming and attacking from the rear end, right? So what happens? This X minus is removing itself and leaving behind a carbon NU bond. So initially the X was present on the like right side, and now the NU bond, a carbon NU bond is formed on the left side. So basically the configuration, if I see, the three-dimensional arrangement is getting reversed or getting inverted. So here what happens, an inverted configuration is observed, and it is a very important point to note in SN2 reaction. Because the bond formation and bond breaking occur simultaneously in a single transition state, the SN2 reaction is called a concerted reaction. Okay, concerted means the one occurring in a single step. The entire mechanism of the reaction is occurring in one single step, and that's why it's called a concerted reaction. This is the mechanism for SN2 reaction. What happens is, this OH minus is coming and attacking the substrate, which is the CH3Cl, methyl chloride, from the rear end. And here at one particular phase, what happens? This OH minus bond is on the verge of formation, and this bond is on the verge of breaking off. So this is the unstable transition state. Okay, this is unstable because here carbon is forming 5 bonds, which is obviously thermodynamically and kinetically not feasible at all. Now what happens here, the Cl minus gets removed off and the bond is formed between the COH, but in the opposite direction. Okay, so the configuration here getting reversed. Okay, now this is the energy level diagram of the SN2 mechanism. The reactants were like this, the nucleophile and the substrate. Then they went on to a transition state, which was a higher energy unstable state. Then ultimately they fell down to a lower energy product, which led to the bond formation between the substrate and the nucleophile, resulting in the removal of the nucleofuge. This is the one for methanol. This is a specific one. You don't have to remember the value. Now if I see the stereochemistry basically means the three-dimensional arrangement. So here what happens, there is inversion of configuration. Okay, initially the chlorine was present on this side, but on the final product there is inversion of configuration. Now the reaction of alkyl halides, if I see, this is the order of reaction. So as I know, as I have already said, these halides are the leaving group, and out of this iodine is the best leaving group. So you don't have to remember these values, you just need to know that halides are better leaving groups. Okay. Now if I see the nature of substrate, okay, now methyl bromide, ethyl bromide, isopropyl bromide and tertiary butyl bromide. Here basically how the reaction is occurring, the nucleophile is coming and attacking from the back side, right? So if the carbon atom on which the nucleophile has to attack is more bulky, that means it is associated to more number of carbon atoms, then the nucleophile has to compete in order to find a site of attack. So if I compare these, gradually if you see the number of carbon atom is increasing, therefore it will be difficult for the nucleophile to come and attack itself on the, this is the carbon atom, this is the site of attack to which the halogen group is directly attached. So as the bulkiness of the carbon atom or the carbon atom on which the nucleophile will attack is increasing, therefore it will be difficult for the nucleophile to come and get associated with that carbon atom. So the order of reaction varies as 1 degree, or the methyl group is highest in reactivity with as compared to, in comparison to 3 degree, because in 3 degree the bulkiness is gradually increasing. So the order of SN2 reaction varies as methyl group greater than 1 degree, 2 degree, and finally least reactive being the 3 degree carbon atom. Now if I see the effect of nucleophile, the alpha carbon in a 3 degree carbocation is less hindered, and these alkyl halides do not undergo, obviously the one which is highly bulkier, it will not allow the nucleophile to come and attack, that we have discussed in the previous video. Okay. Now obviously the one which is having a greater nucleophilic power will attack in a great, it will attack very easily, and it will lead to the removal of the leaving group at a much faster pace. So if I compare the order, then these basically iodine, Cn minus, Hs minus, Rs minus. These are very good nucleophile, and gradually the nucleophilic strength decreases in this order. The nature of leaving group, these all are not important. If we move on directly to SN1 reaction. Okay, if I see the solvent factor, then what happens? It basically requires a polar aprotic solvent. Okay, a polar aprotic solvent is the one which is a very feasible solvent which helps in carrying out the SN2 reaction. Why? Because hydrogen bonding with the nucleophile can occur, which leads to slowing down the reaction. Okay, if a protic solvent is there, then it will lead to hydrogen bonding, as a result of which it will not allow the nucleophile to come and attack on the carbon center. Therefore, a polar bond is required, but that must be aprotic. There must not be any source of hydrogen bonding possible, which will ultimately hinder the rate of reaction. These are some of the examples of polar aprotic solvent: dimethyl sulfoxide DMSO, dimethyl formamide DMF, hexamethyl phosphomide HMPA, and acetonitrile. Next, we'll move on to, if I get a summary of SN2 reaction, then the substrate, if I see the substrate, then the order will vary as methyl, primary, secondary, and tertiary. If I see the nucleophile, then negative charge will be more reactive than the lone pair of electrons, and leaving group, then leaving group which stabilizes the negative charge, those will act as a good leaving group. And if I see solvent, then the solvent must be polar and aprotic solvent. These are certain feasible conditions under which SN2 reactions can occur properly. Now if I see SN1 reaction, now basically it's just the reverse of SN2. What was happening in SN2? The nucleophile was coming and attacking on the backside of the carbon, right, on the rear end. But here what happens, a CX bond which was earlier present, it will break off, leading to the formation of a carbocation and liberation of the leaving group. Carbocation will leave a site of attack for nucleophile. The nucleophile now has to, do not have to compete with any other substrate. It will just come and take the place already made available by the carbocation. So if I see first order, it is only and only dependent upon the substrate. It will not depend upon the nucleophile, because in the first step, it occurs in two steps. In the first step, what will happen? There will be generation of a carbocation. In the second step, the attack of nucleophile. The rate of reaction is only and only dependent upon the first step, which is the slow step or the rate determining step. So here 3-degree alkyl halides are essentially inert to substitution by SN2. Why? Because bulkier groups are present. So as the nucleophile has to compete with a lot of heavier groups in order to find the site of attack for carbon center. Therefore, SN2 was not a feasible path for 3-degree hydrocarbons. So what happened? Because of steric hindrance at the backside of alpha carbon. Despite this, 3-degree alkyl halides do not undergo substitution quite rapidly, but by a different method called SN1 mechanism. SN1 means substitution nucleophilic first order, or I can say unimolecular substitution reaction. It obeys first order kinetics, that is, rate is directly proportional to the substrate. It will not depend upon nucleophile. Now the rate depends upon concentration of only one reactant, the alkyl halide, and not the nucleophile. Now the order of reaction will be reverse of that of SN2, which is 3 degree, greater than 2 degree, greater than 1 degree, greater than methyl group. If I see the mechanism, then what happens is this CBr bond, it breaks in the first step, generation of a 3-degree carbocation. Now once this carbocation site is readily available, then what happens? This nucleophile, whichever it is, in this case it is I minus, it comes and takes the place of the already left nucleophiles. Okay. So basically the reaction step are slower, rate limiting dissociation of alkyl halide forming a carbocation intermediate. The second step is a rapid nucleophile attack at the carbocation. The nucleophile is not involved in the slow or rate determining step. Basically, nucleophile is not involved in determining the rate of the reaction. Now, if I see the rate of SN1 reaction depends upon 3 factors. One is the nature of the substrate, the ability of leaving group, and the nature of solvent. Now always the reaction is dependent upon the solvent. Why? Because solvent is the stabilizing medium. Okay, in this medium only the generated, now here the solvent has to be a polar protic solvent. Why? Because after the loss of the nucleophuse, we will get a carbocation, which is a positively charged substance. In order to neutralize that positive charge, there has to be surrounding negative charge. Therefore, the solvent must be polar and protic. Okay, so there are three factors on which the rate will depend. One is the nature of the substrate, the ability of the leaving group to leave, and the nature of the solvent. The rate is independent of the power of the nucleophile. If I see nature of substrate, obviously 3 degree, 2 degree, 1 degree and methyl group. This is the order. Now if I see stability of the carbocation, then obviously we have discussed in the earlier videos what are the factors which are responsible for stability of carbocation: inductive effect, hyperconjugative effect and resonance if possible. Then all these factors, if they add up to the stability of the carbocation. Now if I see this, we have already discussed. Okay, if I am seeing the nature of nucleophile, then the nature of nucleophile has no effect on the rate of SN1 reaction because it is not involved in the rate determining step. All carbocations are very good electrophiles, that means electron acceptors, and even weak nucleophile like water and methanol will react quickly with them. So basically they are already electron deficient, right? So wherever they find any source of electron, be it weak or strong, they will just grab it to form a bond with it, right? So the two SN1 reactions will proceed at essentially the same rate since they are only differ in the nucleophile. Nucleophile has no impact on the rate of reaction. So whether it is iodine or fluorine, the rate of this addition of nucleophile will be same. Now again, solvent effect if I am seeing, then for SN1 reaction the solvent affects the rate only if it influences the stability of the transition state, which is the generation of carbocation. The nucleophile is not involved in the rate determining step. So polar solvents, both protic and aprotic, will solvate and stabilize the charge transition state, lowering the activation energy and accelerating the SN1 reaction. So the solvent has to be polar in order to stabilize the resulting carbocation. Therefore, non-polar solvents do not lower the activation energy and thus the SN1 reaction is generally slower. Okay, so these reactions proceed in a polar solvent over non-polar solvents. This is the general reactivity of the in different solvents. Yeah, these are some examples of polar solvents: DMF, HMPA, we have discussed in the previous slides. Then reactivity of alkyl halides towards, if I see primary, then what happens? It is mostly predominantly showing SN1 reaction over SN2. We will for now not be taking up E1 and E2. For now we will just be focused on SN1 and SN2. So here what happens? In primary halide, SN1 does not occur because it is SN2 is highly favored as the alpha carbon is available for the nucleophile to be easily attacked on. Therefore, it will undergo mostly SN2 mechanism and SN1 is not pretty evident here. In case of secondary, SN1 can occur under solubilisis condition in polar solvents, but SN2 is favored one because here also obviously there are steric hindrances but not that evident as compared to tertiary. Now if I am saying tertiary, then SN1 is highly favored and SN2 does not occur at all. Effect of solvents we have already discussed. Overall summary of SN1 and SN2 because E1 and E2 we are not seeing. So if I am seeing methyl, then it obviously there is no steric hindrance. So it will be pretty evidently showing you only SN2 reactions. SN1 reactions will not be shown here. And if I am seeing primary, then here it mainly gives SN2 again because it is unhindered. The alpha carbon is unhindered over here. If I am seeing secondary, then obviously there are chances of both SN1 and SN2, but predominantly SN2 will occur because there are also less chances of hindrance. Tertiary, this will primarily show SN1 reactions. Elimination reaction, for understanding elimination, we will take up another video. So in this lecture, I guess you were thorough about SN1 and SN2 reaction. This concept will be highly important when we will be studying alkyl halides and aryl halides, and this reaction mainly helps in understanding the mechanism of the organic reactions. So I hope you understood this. Thank you for watching this video. Thank you very much.